Okay, there we go. Today we are covering chapter 21, which deals with optical systems. Largely this means we've got combinations of lenses, but it's any kind of application of using the lenses to do things. Lenses and mirrors, for that matter. So, now that we've dealt with how a single lens forms an image, whether it's real or virtual, and a single mirror forms an image, what happens when we put two of them or more in combination? Okay, right there I've just made a telescope, for example. So how can we predict what they'll do? Let me draw a quick sketch of something. No, I'll give you the rule first. The rule is that when you've got two or more lenses working together, start with your object first. So let's say that the object is this over here. Here's your first lens. You work out, you don't worry about any other lens, you just take the first one by itself and the object. You work out where the image will be from the first lens. Whether it's real or virtual doesn't matter. Then, for the second lens, the object will be the image formed by the first lens. And you don't worry about the existence of the first lens or any other lens or mirror in the way. So now you've just got the first lens's image and your second lens, and that forms a new image somewhere else, maybe virtual, maybe real, and it might be, if you've got a third lens over here, it might be somewhere over here even. Doesn't matter. You don't worry about the existence of any other lens. And you keep working that on through, one lens at a time, where one lens's output, its image, is the input, the object, for the next lens. So, let me give you an example then of a telescope. A telescope that is designed to project a real image onto film. Okay. There's my optical axis. Let's say that I've got the object. Now, where is my color chalk? Here we go. So here's my object. By the way, for convenience sake, so I don't have to write too many letters, I'm going to start using the letter O, capital O, to refer to the object, and a capital I to refer to the image. Okay, let me make sure I know where the edge of the screen is here. Okay, so there's my object, called an red. Now, let's put two converging lenses, just like those double convex lenses I just used. So I have the first one be maybe somewhere like this. All right, and I'm going to have a relatively long focal length here. All right, those two dots are the focal length of this lens. Now, as you'll see sometimes in my notes, because there are focal points for several different lenses all in combination, keeping track of which focal point belongs to which lens can be tricky. I could label them with a lot of subscripts. If this is lens 1, that's going to be F1, that's going to be F1. But also what I sometimes do is put braces that bracket the focal points and a lens together, group them together. Okay, so the image formed by this one. So let's take the first principal ray, which is the parallel ray. Goes in parallel and goes out through the focus, through the far focus. Second one, now I could do the I'm going to go straight through the axis. That's actually the third principal ray. I'm not going to draw all three of these because it'll save some time. but in practice when you're doing this you want to. I'm doing this freehand and I'm really going to be making some mistakes here, but this is just for a general illustration purpose. All right, so here is the image, a real image formed by the first lens. Maybe I'll call that I sub 1 for the first lens's image. Now, a second lens. Let's see here. I think I want to have this be a short focal length lens, converging again. Very short focal length. There's the second principal ray. Third axial ray. There's the second, and the first should, yeah, it's pretty close. Something like that. So, if you can't quite see that, let me turn the camera just a little bit. There. There's the image, the real image formed by lens 2. So now if I put a piece of film here, now I've got a magnified image of the object. Okay, so that's how these things work in combination. The output of the first lens is a real image here. That's the input for the second lens. Now, what if I had had a virtual image from the first lens? What if the virtual image from the first lens was here, and then I've got this second lens here? What you do is ignore, once you've found the virtual image, okay? When you do the ray tracing for the next, you ignore the existence of that first lens. It's like it's not even there. You don't have the light rays, when you're doing the ray tracing for the second lens, from its source, its object, to the second lens, you don't have them passing through, refracting to the first lens again. It's as if it's not there. Okay. Now, let's see where I put this. So you can work out the combinations of these either with ray tracing, as I've done here, or by using the thin lens equation. 1 over the focal length equals 1 over s plus 1 over s prime. 1 over the object distance plus 1 over the image distance. Make sure you keep track of your size. All right, let's see, cameras. Let's deal with cameras here. All right, the first thing we've got to deal with for cameras is the idea of the effective focal length. Now, the effective focal length, whenever you see effective on some term in physics, what it means is that it's not strictly speaking what we're dealing with, but it works that way in practice. So what I mean is that when we have a combination of 2 or more lenses, let's say if you ever do any photography, the lenses, the interchangeable lenses on an SLR camera. SLR stands for single lens reflex. And these are generally the cameras where you see they're a little bit bigger than a pocket camera, and they've got interchangeable lenses that stick out a bit ways. SLR, or the modern version, you see DSLR, that just the D is digital, but it works the same way. Single lens reflex means that you look through the camera lens, which is usually, about yay big around like that, and it's got several different lenses in there. The single lens reflex means that when you snap a picture, your viewfinder is working through the same lens as the image that will be formed. So you see exactly what will appear on the film. there's a prism inside, or a mirror, that will allow the light to go through the viewfinder normally, and when you take the picture, snap the shutter, that prism or mirror flips out of the way, and the light is exposed onto the film, or the digital chip. So these, the lenses for those are all combinations of lenses, never a single lens, because we get to the point where we can get very good, sharp images with color correction and so on like this. So let's say that we've got a converging and a diverging lens here. Now, I'm not going to draw the principal rays here, but just to show you in general what's happening. If you have parallel rays coming in, okay, the converging lens makes those converge towards the optical axis, and they would meet at the focus, the focal point of that first lens. Let's say that it would be going here. That would be the focus of the first lens. What does a diverging do? Parallel rays coming into a diverging lens diverge away from the optical axis. Now, if they're already converging by a bit, then they're going to converge more slowly, or they might diverge, depending on the strength of that lens. So in this case, maybe it's going to be something like this. I said maybe because I don't know unless I were to work out the ray tracing details on this. Now, these two lenses working together, there's the focus of the first lens, and you see that it winds up lengthening the combination of these two as a longer effective focal length as this single lens does by itself. So, if we were to try replacing these two lenses with a single lens that would bring it to focus here, and if we put that lens at the midpoint of this combination, so right like that, I can draw it converging because we see that the effectiveness is to make it converge. Then, okay, a single lens placed at the midpoint here, which brings the image to a focus at the same point as that combination does. This distance here would be called the effective focal length of this combination here. And so, whenever I talk about a single lens or a combination of lenses, and I mentioned the focal length, if it's a combination, we're talking about the effective focal length. Okay. Now, let's see what happens when we've got the magnification, the magnifying power of distant objects. And again, generally we're talking about camera lenses here, because they are labeled by their focal length. There are really two numbers that are probably important when you are choosing between different camera lenses. One of them is the focal length, or the effective focal length. And I'll show you what that affects. The second one is called the F number, or F ratio. It relates to the aperture size. And I'll get to that afterwards. So, if I've got, let's see here, talking about magnification now. Let's say that I have a near object. Let's see, here's the lens. There are the focal points, the near and far focal points. If I have a nearby object, looks about right there. There's my image. But if I have a distant object, let's make those focal lengths be the same. The focal length be the same. Okay, I want it to be the same size. for the same object and the same lens, where the only difference is the distance to the object, as the object moves farther away from the lens, the image, the real image for a converging lens, moves closer to the far focal point. So this distance here is f. And the distance from the lens to the image is s prime. The distance from the lens to the object is s. So as the object distance increases, the image distance, s prime, doesn't just decrease, it approaches f. So for an object which is infinitely far away, the image distance would be equal to the focal length of the lens. Which brings us back to the idea that an object infinitely far away would be emitting parallel light rays parallel to the optical axis. And we know that those converge at the focal point there. Also, you see that the image becomes smaller and smaller as we get farther away. You can see the same thing if you look at the thin lens equation. All right, recall the thin lens equation there. 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. Now, as s increases to infinity, let's see here. How do I work this? S approaches infinity, then 1 over s approaches 0. That's a good way to put it. Then that means that 1 over f becomes about equal to 1 over s prime, and for that matter, as we cross multiply, f is about equal to s prime, as your object becomes very far away. Now, in terms of magnification, we get an interesting thing then. Remember that the magnification equation is that, this is called the lateral magnification, meaning how long the object is, how high it is. It's negative s prime over s. Very important equation. Now, minus 1, because of the inversion, times the image distance over the object distance, or for that matter, the image height, minus 1 times the image height over the object height. We get the same result. Now, if you have your object infinitely far away, we talk about an object at infinity. And really what that means is just that it is very, very far away in the limit of s approaching infinity. So if you put that in here, then the focal length is about equal to the image distance, and m becomes about equal to negative f over s. Okay. For that matter then, notice that if we take the absolute value of this expression, the magnitude of the magnification is proportional to the focal length. So, for objects at infinity, the focal length is an important characteristic of the lens that tells us how much the object will be magnified by. The magnification is proportional to its focal length. Now you're going to know other things as well, object distance and so on, to know what the actual magnification will be, but you know it's going to be proportional to. So, let's say, this gives us a way of comparing lenses. We've got 2 lenses. One is a 20 millimeter focal length lens. Let's see. And the other one is an 80 millimeter focal length lens. You know that the 80 millimeter focal length lens will give you a greater magnification than the 20 millimeter one. And for that matter, for the object at the same distance, it's not really at infinity, it's just very far away, an object at the same distance, you can see that the magnification will be exactly 4 times as great for the 80 millimeter lens as the 20. What we do is we take a ratio. If magnification, absolute value magnification, because of the equation, is proportional to focal length, then the ratio of the magnification of this one to the magnification of that one is the ratio of their focal lengths. 80 divided by 20 is 4 times. Now, if you have what's called a zoom lens, that's an adjustable one that you can change the focal length like this, and you can see the lens moving in and out. If your zoom lens has a range of focal lengths from 20 out to 80 millimeters, it's actually pretty typical for kit lenses that are delivered with an SLR camera. Then, that would be a 4-power zoom lens because it covers a range of 4 times in magnification. Okay, now, the other number that's important on a lens is the aperture, the F number or F ratio. Now, this one is trickier, and there's a little bit more math to it, but also we're not as accustomed to the concept. And the third reason is that the notation is inherently quirky. In fact, it's often confused me too. So, I'll understand it takes you a little bit of time to get used to this. The aperture. This gets us to the intensity of light gathered by the lens under certain lighting conditions. So first of all, let's think in terms of what intensity is. Intensity is flux. Now, your textbook doesn't use the word flux ever, actually, which is unfortunate because that is a term that we use in physics. But flux is how many photons of light, how many light rays per time per area. So if I put this in here, intensity, I, is equal to the amount of energy in the light ray, so energy of light, per unit time, per unit area. I'll put that as a definition. So really, I is defined as the energy of light delivered to you per time per area that it's hitting. Now, let me draw this as a picture. The intensity of some source of light coming down. Let's say that I've got this little bit of area. This could be a piece of film, for example, or a light detector. Now, this that I'm measuring it over is that unit of area. It is a small amount of area, so that's A there. And if you count up the light rays, let's imagine that, let's see, two light rays have the same energy if they have the same wavelength. Two little packets of light have the same energy, they've got the same wavelength, the same frequency, which is equivalent. So let's imagine what they all do for a moment. So all we have to do is to count the number of light rays to know the amount of energy we've got. Now, this is how many also per time. So you can imagine that right after that, there's another second's worth of light rays coming in. So if I take how many light rays per second per bit of area packed in here, okay, because they're coming all over like this, but I want to count up how densely packed they are. Light rays are coming down all over the place. Okay, that's the intensity. Now, I could have, if I had the same total number of light rays, but they were spread over a wider area, you see then the intensity would be lower. If I had only 1,000 light rays and I spread them out over the whole room, you couldn't see anything. But if they were all concentrated into a very narrow beam, In one spot, you would say that that was a very intense beam of light. For that matter, if you had 1,000 light rays delivered in a nanosecond in that little intense spot, that might be pretty bright. But if it took a week for those 1,000 light rays to hit that same spot, it would be a very dim light. Okay? If you're dividing by a larger unit of time. For that matter, if you had, for the same amount of time and same area that they're concentrated into, if you had 10 light rays, the energy would be lower, so the intensity is lower. But if you had 1 billion of them, the energy is higher, so the intensity is higher. That's the concept. It is the density of light energy, the area density, as they cross through this, and the how much time that number takes to go through. Okay, given that, the exposure of a piece of film or of the camera chip, for example, the exposure is determined by, so what that looks like, how well exposed it is in the picture. Per pixel, for every little bit of area on the image, is determined by the total amount of energy that reaches that pixel. Now, if a pixel has a defined amount of area, then what we're really talking about is how much energy per time reaches that pixel. And you can control that. If your lens can gather more energy in a certain amount of time, then it's what we call a faster lens, because you don't need to expose it for as long to get the exposure you need. But if it only delivers a small amount of energy per unit of time, then you need to compensate for that by having a much longer exposure to get the same number of photons hitting the pixel. So let's take a look. How does a lens gather and concentrate the light? So a bigger lens gathers more light. If you've got the same density of light rays coming in, okay, this small lens here gathers, 3 of those maybe into a little bit of area. And we've had them separated out and not at a point here. Okay? Whereas this big lens gathers a lot more. This one produces the more intense image. So, if we look at the intensity of the image, I probably abbreviated IMG from now on, is clearly then proportional to the area, the cross-sectional area of the lens. Now, I should say cross-sectional. I've drawn an edge on. What I really mean is the area that the light sees coming at it. So this one is bigger than that one. Image is proportional to lens area. Now, the lens area, if it's a circular lens, then that means 4 pi r squared, or that pi r squared, but the radius is half the diameter, so that's pi diameter over 2 squared. Pi and 2 are just constants, so I can drop them from the proportionality, and the intensity of the image is proportional to the lens diameter squared, because area is proportional to diameter squared. Okay, therefore the bigger the lens, the brighter the image will be. That's one of it. The second thing is, the focal length plays a role as well. So the same amount of light focused into a smaller image is going to make the image brighter. So think about that. If I've got a lens with a long focal length, it'll wind up making a larger image. But for the same size lens, with a short focal length, the image is going to be smaller. When you think about, oh, I want it to be larger? Maybe you care about magnification. But if you make the image smaller, then there are more photons per pixel, more rays of light per pixel. Therefore, the image will be brighter. So it's a trade-off between magnification and on image brightness exposure. So the intensity of the image is inversely proportional to the area of the image, not the lens, the image. 1 over the area of the image. It's two-dimensional after all on the film. So, the area of the image is proportional to any linear dimension of the image, like the image height. So, area of the image is proportional to h prime. Remember, that's what we use for the height, and prime means for the image. Oh, squared. Because that's a single axis of the image there. Okay, that's the height of the image squared. Now, the magnification. Magnification is negative because of the inversion, h prime over h, image height divided by the object height. That's equal to minus image distance over object distance. And for an object very far away, for a distant object, recall that that's about equal to minus focal length over object distance. That is, the image distance becomes about equal to the focal length. And therefore, you're going to have your real image cast up at the focal point. That lens. Looks like a long train of thought there. But that means that, okay, therefore, dot, dot, dot means therefore. H prime is, proportional to the focal length. H prime is proportional to the focal length. Notice I didn't say it's about equal to because I've got different denominators here. They're both proportional to the magnification, therefore they're both proportional to each other. All right, given that, the area taken up by the image is proportional to focal length squared. By the way, notice because I had this prime on the h, when I wanted to square it, I put parentheses around it, because otherwise it might look like a 1 and a 2. And that'd be confusing, 12 or something. So I can drop the parentheses. All right, now, so the longer the focal length, the larger the image will be. It's intuitive. You saw it when I was doing ray tracing after all. And you can see it from the thin lens image. Now, this means that the image intensity is proportional to 1 over the area of the image, so it's proportional to 1 over focal length squared. Now, so let me show this thing. If I've got the same area of lens, remember a thinner lens, one with a shallower, a flatter curvature, will have a longer focal length. So the light coming into this one with a short focal length will make an image that's, say, that big. We're looking at slightly longer image. But one with a longer focal length will make a bigger image, but you have the same number of light rays spread over a wider area, so it's less intense. Therefore, it's a fainter image. Okay, now let's put these two things together. This together means that the image intensity is proportional to d squared and inversely proportional to focal length squared. So, the image intensity is proportional to diameter of the lens divided by the focal length. What are we going to use that for? Let me erase this and I'll show you. Keep that thought in mind. Image intensity is proportional to lens diameter divided by focal length. By the way, I did have the squares on there, but the thing is, I'm not sure I really justify dropping the square term there. Nevertheless, the bigger D into F, D over F gets, the bigger the intensity will be there. Whether it's squared or not, it's still going to be true. I've got to make a change in my notes. All right, now with that in mind then, it's therefore also proportional to 1 over the inverse of this, F over D. Now, let's call focal length divided by distance, divided by lens diameter. We're going to call that the F number. Sometimes written F/number, that is not F divided by some number. This is a quirky, weird notation, but it's consistent in photography, so we're just going to get used to it. The book writes it F-number, but that's a lot for me to write by hand, so I just use the traditional notation, F-number. F-number is defined as focal length divided by lens diameter. Okay. Focal length over lens diameter. This is a physical property of the lens, or of the lens combination. This lens has a relatively long focal length. There you can see some of the image of that up there. And it has a wide diameter. This one, has a shorter focal length and a smaller diameter. So if you want to compare their F numbers, you'd have to divide those out, and you'd find out what the F number of the lens is. Let me show you how we use that. This means the image intensity is inversely proportional to the F number. I'm putting that in parentheses so it doesn't look like you're dividing by some other number there. All right, make sure you remember this F number definition. The bigger the F number, the fainter the image that lens will be, or the lens combination will be. The smaller the F number, the brighter the image will be. Doesn't mean that it'll be a large image, but it will be brighter anyway. So maybe we've got what you might find in a fairly typical range of F numbers. For an SLR camera zoom lens, you might find that it ranges from, here's again the notation, F number equals, say, 2.5 up to maybe 25, rounding off. I think mine goes up to like 23. This here, and this is written, by the way, again, the notation. This is written as, I'm putting it in quotes so you know it's not an equation, F/2.5. And this would be written F/25. But what it means is the F number, this ratio, is equal to 2.5 or equal to 25. Keep it straight. Practice this. Now, the F2.5 is going to be what we call a fast lens. Because the 1 over a small number gives you a large number. 1 over a large number gives you a small number. So this would be called a fast lens, that would be called a slow lens. What are the uses of that? Well, the fast lens is great when you've got low light situations. You don't have a lot of light coming in. And so you need to capture every photon you can. Well, let's say you're in dim light. There are two things you can do to expose your picture properly. One, you could just take a longer exposure. If you're in dim light, just hold the shutter open for long, maybe half a second or something. But that might work fine for a still image where nothing's moving and you've got a tripod. But what if you can't? What if you need a 1 second exposure? Think of how long a second is. Though that was 1 second beats. How still can you hold your camera over that long time? If you've got where you're zooming in really well, really a far distance, you're going to be shaking. You're going to see the shaking there. So maybe a longer exposure doesn't work. What you could do is to change the f number on your lens and go out so that you have a wider aperture. It gives you a smaller number. Okay? If you increase the lens diameter, well, you can't increase your lens's diameter. But in practice, what they do is, let's say that your lens, this is a 3/4 view. There is your combination of lenses. All right? And you have what's called the iris here. And it's a series of metal, I won't say baffles, but they're little metal slides that cover over parts of the lens. And so it only allows light in through here. So this effective diameter of the lens is the part of the lens that light can actually go through. Anything out here can't go through the lens. So effectively, the lens that's inside here is smaller than as you start to close that up. That's how your camera changes the f number. And it also, you can change the focal length. A longer focal length is a larger f number. Shorter focal length, smaller f number. Combination of those two is what gives you the f number you need. So if you go for an f2.5 in low light, that's better than trying to do f25 because it's going to be a very faint, pixelated image. Okay. There are other effects too. For example, I didn't cover it, but there's what's called spherical aberration. There's chromatic aberration. The outer edges of the lens can often distort the image. And the inner area of the lens, where the thin lens approximation works best, gives you the sharpest picture. So if you, what we call stop this down, these are called f-stops sometimes if you have it where it can click into place for different f numbers. If you go down to a smaller aperture, then you can get a better looking image. But your f number becomes larger, so your intensity of the image is fainter, and therefore you need a longer exposure time. Okay. Now let's take a look at vision. How does the human eye work? Okay, the eye. In cross-section, the eye looks kind of like this. It's more or less spherical. Inside of it, you have some muscles, and you have the lens. I'll draw the lens in blue. Which is a little bit squashed looking compared to what you might expect from the lenses we have here. You've got this stuff that holds the lens in place, and then muscles that control the shape of the lens. And then over here, this part bulges out a little. There we go. So this is called the cornea. It's transparent. Then you have a transparent fluid, jelly-like, but it's basically a fluid, called the aqueous humor. Now, there is a lot of refraction that happens as light rays go from the air, through the cornea, into the cornea, and through the aqueous humor. The aqueous humor has an index of refraction of 1.34. which is very, very close to that of water, which is 1.33. Then you've got the lens. The lens has an index of refraction of about 1.44. Okay, so there's not as much refraction happening as they go from the aqueous humor into the lens. The lens's index of refraction is between that of water, 1.33, and glass, about 1.5. Now, then you have, in the larger part of the eye, something called the vitreous humor. Now, humor is an old-fashioned word in medicine for bodily fluids. They used to have the medieval and even classical, I think, theory of the 4 bodily humors, blood and phlegm and bile and so on. So that's where the term comes up. It doesn't mean funny, it just means liquid. Okay, so the vitreous humor, which again has an index of refraction of 1.34 inside here. And then finally, you have nerves, sensors that cover the back side of the retina, back side of the lens, and this is called the retina. And then there's a connection here where that information is taken to the brain, and that's called the optic nerve. Okay. Now, the diameter of the lens is about 1 inch, almost precisely 1 inch, which comes out to be about 24 millimeters. Okay. You've also got another thing here. Surrounding the lens and inside, between the cornea and the lens there, you have muscles that are able to pull around an iris, out the real iris. What we use in the camera of the iris is an analogy to the iris in the human eye and of other animals. And the iris then is able to block light from going through the lens. So in bright light, the iris contracts, and the opening, which is called the pupil, gets smaller, allowing in less light and changing the F number of your eye. In dim light, the iris expands and the pupil gets bigger, and it allows more light in. Okay. So as I said, most of the refraction takes place at the boundary between the air and the cornea. And you can see that the cornea is bulging out of it, so it's not at the same radius of curvature as the rest of the lens. The lens itself, the rest of the eye, the lens itself, because it is able to change shape and therefore change focal length, is used for fine-tuning that. So even though most refraction takes place here, this is where the adjustments take place. Okay. The range of F numbers for the lens, for the eye, given that you have a pupil diameter that ranges from about 1.5 millimeters when the pupil is very small in very bright light. The diameter of the pupil increases from there to about 8 millimeters in dim light, where you're dark and active. So, if you take the focal length as being about 24 millimeters, obviously it's a little shorter than that because of where the lens is, but the whole system here, from here to here, is what we're measuring. The range of F numbers then goes from F, focal length, what are we talking about? F focal length divided by the diameter gets you F16 up to about F23. F3. And this is actually pretty similar to the range of F numbers in a lot of camera lenses. So it's not something wildly different, even though the system is much smaller and with a much shorter focal length, you get a similar range of F numbers. Okay. Now, the eye adjusts the shape of the lens for when we have distant objects that are closer or farther away. let's say that we have a distant object over object. Here's our lens. I'm going to draw the actual shape rather than a symbol. And then here is our retina, okay, which is curved there. So, for a distant object, blah, 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 goes through, you wind up with a your image here, eye. But for a close by object, all right, in order to focus the light onto a retina that's the same distance away, we have to change the shape of the lens. We have to change the focal length of the lens. This is no longer an object at infinity. And so you have to have a thicker lens in order to make the image distance be the same. So, the lens thickens up to shorten its focal length when you have an object nearby. The process of doing this is called accommodation. The lens changes shape to accommodate the distance to the object you're focusing on. Now, we have a range of distances that we are able to see objects clearly. The farthest that we can see an object would be called the far point. And that's determined by how thin the lens is able to be made. In a normal eye, the far point is at about infinity. So we can see objects that are very far away sharp, to a reasonable degree of sharpness. Idea of 20/20 vision and all that, I won't get into here. On the other hand, the closest that an object can be, and still our eye can accommodate it and bring the image, the real image, to focus at the retina, is called the near point. Actually, we use FP for far point and NP for near point. Now, for a normal eye in an adult, and the range of near points changes as you get older and from one person to another. Let's see here. I don't actually have this written in, but I think it was about 25 centimeters. So about 10 inches is a typical near point for an adult. Okay. When you get older, your eyes tend to have less accommodation that they can handle. And so this is when you start needing reading glasses, for example, and so on. Now, the two kinds of common eye problems are hyperopia, farsightedness, and myopia, or nearsightedness. Hyperopia, what happens in farsightedness is that the eye is too short. The distance from the lens to the eyeball, from the lens to the retina is not long enough for the real image of a distant object to be cast onto it. And what happens is, distant object over here, rays come in, that, and your image would come to focus behind the retina, but it can't because the retina's in the way. And so the light rays here don't meet up, and you get a blurry image there. Now, for a nearby object, your eye is able to accommodate and to bring that to focus at the retina, but not too far. Again, it's a biological issue. So, what you do then is, for far objects, you want to put in place a corrective lens, eyeglasses. which will take the object and will create a virtual image of it that is closer to the eye. So what is done then is that you have a converging lens. Here's your distant object. The light rays going through this converging lens, okay, see what appears to be a nearby, let's see, a closer object. Okay, there's the image. They create a virtual image that's closer and actually, in fact, a bit smaller. I've drawn it a bit too big there. Let's see. Oh. Anyway, the virtual image is closer by, and then your eye is able to bring that focus on the retina. Now, the opposite problem is called myopia, which is nearsightedness. Oh, good grief. I switched up my what I wrote. Go back here. I thought something was off. Farsighted means you can see far things, but not nearby things. All right. Aside from that, everything was fine. Well, a nearby object, the explanation is correct anyway. An object that's closer than your eye's, poor quality near point cannot be brought to focus on that spot there. All right, it will be brought to focus behind it. So you install a corrective lens. That's why my ray tracing didn't work. That's your correcting lens. It is a converging lens. Here's your image, too close by to be really useful. Here's your object, too close by to be brought to focus in the correct spot. But when you trace the light rays here, okay, now let's trace those back, and it produces a upright, magnified, virtual image that is farther away. Now the light rays from that go into your actual, your eye's lens and make a properly focused image on the retina. Okay. Corrective lenses for farsightedness are converging lenses, like a magnifying glass. And it makes the virtual image upright, magnified, and farther away. Nearsightedness is the opposite problem. The problem is that you can't see things that are far away. You're able to see things near. You are nearsighted. So I'm nearsighted, all right? And I'll show you how these glasses work. So let's say you've got your object that's far away. And there's the retina. And your image would come to focus too close there. So when the rays actually hit the retina, then they are out of focus. So what we do is we install a corrective lens, and it is a diverging lens. It's thinner in the middle, thicker on the edges. Now we have our distant object. Light rays come in, they diverge a bit. Okay? And that means they appear to come from this virtual image here, which is closer, and it's within the range that your eye can focus. And so then the light rays come out here, they come on down and you get a properly focused image on the retina then. Divergent lens. So, reading glasses are for people who are farsighted. They have trouble seeing a book close up with a reading. So their lenses are converging, which means they're thicker in the middle, which means they're basically magnifying glass lenses. And you can tell because if you take reading glasses, you can cast a real image with them onto a piece of paper. But for nearsighted people, these are diverging lenses of the corrective ones. If you try to cast an image on the paper, you've got nothing, because the rays are diverging, not converging. So that's one way you can tell the difference there. Okay. Now let's take a look at magnifying glasses and briefly microscopes and telescopes. Okay. We've already talked about the lateral magnification. If an object is 3 feet high, but the image is 1 inch high, you've got that ratio of 1 inch to 3 feet, gives you the lateral magnification. What about the angular size? What angle the object and image subtend? That is often a more useful property for us to know. So if you are, there's your eye, looking at it from the side, okay? Eyelashes up here and below, there's the side of the eye. Physics symbol for the eye. If you are looking at some object out here with a height h, and a distance, object distance s away from you, and there's a ray that goes to the top on it, and there's a ray that goes to the bottom on it, this makes a right triangle. What we're asking is, what is this angle? We'll call it theta. This is called the angle that the object subtends. What angle it spans from the base to the tip. And it depends on the distance, of course. If it's closer up, it's not here, then you get a larger angle. All right. So if you want to see something and see details on it, natural thing is to hold it closer. But you can't really get it any closer. You can't do anything useful with it closer than your eye's near point, 10 inches or whatever it is for your eye. So let's take a look at what this angle is. Now, the tangent of an angle is equal to the opposite over the adjacent side, h over s. We'll deal with small angles for now. So for angles much less than 1 radian, the tangent of theta is about equal to theta. And therefore the tangent of this is equal to h over s. The angle is equal to h over s. The object height divided by its distance. Again, in radians. Just convert it to degrees if you need degrees. Okay. So the angle it would subtend at the near point, if it's 10 inches or whatever, 25 centimeters or whatever away from you, would then be theta sub near point in P would be equal to the object height divided by that near point distance. The book goes on and fills in 25 centimeters, but that's not true for everybody. Now, let's say we've got a lens. If we want to see it in more detail, we can try magnifying it. All right? What good does that do us? Well, I mean, what is magnification in that sense then? A magnifying glass is used in a way such that, let's see here. You see the image of those lights cast onto this paper? So if I put, that gives me a rough idea of where the focal length of the lens is. Of course, the object is not at infinity, so it's not really there. But it's pretty close. Now, if I put my eye, if I put the lens, if I put the object, paper, closer than the focal length of the lens, and I look at it, I see things magnified. Why? Because, let's see, optical axis, the lens, apparently slightly bent, the object of height h, no, wait a second, wait a second. Yeah. So, if I've got focal length here, and I put the object inside that, and I trace the rays in, let's see. Over there. Okay. Now, apparently they're not converging going out here. That means they are diverging from a spot about there. Now, if I put my eye here, do I get a better view looking through the magnifying glass or by taking it away and looking at the object? You see, what happens is it creates a virtual image because the object is inside the focal length. I get a virtual image that's farther away, so I can make it beyond my eye's near point, first thing. And it's larger. But does it look larger? Take a look here. The angle from the center of the lens out to the object is, well, that's one angle. And that's equal to the angle from the center of the lens out to the image and up to the top bar there. Okay. Now, the distance of the object height h, let's see, this is h prime, this is a distance, object distance s, and this is an image distance s prime. Okay. The angle is h over s, which is equal to h prime over s prime. That's easy enough. Measured from the center of the lens. And if you move the object closer to, moving it away, closer to the focal length of the lens, you can see by doing it. Let's see, no. Yeah. Moving it farther away here, the image would get farther away and would get even larger. There we go. So, what you're interested in is what this gets you. The magnification, the angular magnification, then will be defined as the ratio of this angle here divided by the angle the object, the same object would subtend at your near point. The closest that you can comfortably look at something. Now, let's plug in actual numbers. Plug in the formula here. That is, let's see. If we were to move this to the focal length, then our image would be infinitely far away when the object is at f. And it would be very, very large. It would really be infinitely large. It would have a height of infinity. But the angle would not be infinitely large. So, we put that in then. It would have, the object would have a height equal to h, and a distance, the object distance s would be equal to the focal length, divided by what we would get at the near point, and have the same height when it will be at the near point. Cancel out, F near point. What is that? Cancel out the h's and we get the near point distance divided by the focal length. Okay, so that gives us the angular magnification of this, being what improvement do we get, how much bigger does the object look, put at the focal point of the magnifying glass versus holding it at the near point for your eye. So it's inversely proportional to the focal length. The shorter the focal length, the greater the magnification will be compared to naked eye. All right, now let's put lenses in combination and make a microscope first. Now, a compound microscope means that it has two or more lenses. The first microscopes were just magnifying lenses. That's called a simple microscope. And the best of these, back in the 1600s, by Anton von Leeuwenhoek, could produce magnification powers of about 200 times. In fact, they were better than the compound microscopes of the same era. You'd think you could get greater magnification with two of these, and you can, but the quality of the lenses was rather poor then. Von Leeuwenhoek had a wonderful idea for making his lenses by melting beads of glass that would make almost perfect spheres, and then he could slice off half of them. Whereas his contemporaries were trying to grind their own lenses and were not able to get as perfect a shape. I'm not going to go into detail on microscopes and telescopes, but I'll show you the basic idea. For the microscope, you're wanting to magnify the angular size of a nearby small object. So let's make our optical axis be vertical, because we tend to use it that way. Here's our object. Now, our first lens is called the objective lens because it's near the object. It will have a short focal length. That's the key thing. All right, and the object will be just beyond the focal length of that lens. Okay. Now, I'm not all that confident in my ray tracing here, but that's not bad. Okay. So the objective lens creates an inverted real image here. Now, the next lens is called the eyepiece. The eyepiece, if we were making a telephoto lens for a camera, which is basically a telescope, but the idea would be that we want to cast a real image, large, fairly large, onto the film. But for an eyepiece, we're making an image in the eye, you see. And the eye has its own lens. So what we're going to do with the eyepiece, both for a microscope and a telescope, is we're going to want it to make a virtual image that is very large and magnified and very far away, effectively at a distance of infinity, because that allows the eye to relax and not try to focus on something very, very close, which is what's painful. Okay, so our eyepiece then is going to have the focal point be right here. Because you know, if you take a magnifying glass, it'll be another converging lens. Both of these are converging lenses. If you put the magnifying glass, if you put the object there at the focal point, you get light rays that come out parallel. We want them to come out parallel to each other, but at an angle to the axis so that it magnifies this virtual image. So let's say that we've got a focal length that is like that there. Eyepiece because it's close to your eye. Now, the light rays here to the extent I have drawn this correctly, pretty close, these rays come out parallel, but they're really appearing to diverge from a virtual image which is infinitely far away and whose tip is going to be at this angle here. So our eye here gathers these rays in, and it appears to see a very large object but very far away, so it comfortably relaxes the eye, and it's magnified. Magnification then is the ratio of this angle, theta, the angle generated at the eyepiece, to the virtual image of this here. That's the real image, but it makes a virtual image way up there. To the angle from here to this, to the very tiny object, and that gives you the magnification. So you draw another line from here over to there and compare those two angles. Okay, and in this version of a compound microscope, both of these are converging lenses. You can always put in some diverging lenses that do some nice things to reduce aberrations and so on, but this is the basic idea. Now, a telescope. Telescope's a funny thing. After all, biology makes do with magnifying things that are close by but small. So a simple magnifying glass lens can do quite a lot, at least when you're starting off. But it is not possible for a magnifying glass to magnify distant objects, things that are farther away than the focal length. So how do we study distant objects then? How do we study stars and galaxies and such? And it took until the year 1608 before people figured out how to do this. 1608 is the year the telescope was invented, not by Galileo Galilei. It was invented by a Dutch lens maker whose name I've forgotten, but we do know who it was because he applied for a patent for it. And it was during one of the various wars when Spain was trying to conquer Holland. The Dutch were very good lens makers. And he had figured out how to make this telescope, and they wanted to use it to see Spanish invasion ships from a long way off. He wanted to get a patent on it, but the Dutch king was telling him he didn't want to give him a patent because if they published the details then, as you do with patents, then the Spanish would know that they could see the ships from far away. So, but anyway, we know about this now. Now, the next year, Galileo Galilei in Italy read a description of this and decided to make his own telescope. And he was the first one to do a systematic survey of the skies, the heavens, using a telescope. Not the first person, not the first astronomer to use the telescope. Thomas Digges in England had done work slightly earlier, a few months earlier. But Digges never published anything and didn't really follow up that much. Galileo published and he followed up on the results. And that's what made him the great astronomer. Okay. Now, since a single magnifying glass is useless beyond its focal length, for objects beyond the focal length, we need two or more. A basic telescope let me show you, if you're not focusing on something that's infinitely far away first, and then I'll show you what happens when it does go infinitely far away. Let's take our distant object here. Our first lens is the objective lens again because it's next to the object. It'll have a relatively long focal length, although the actual focal length depends on how you design it or what you want to do with it. Okay, this creates a real image that's inverted here. Now, our second lens, is the eyepiece. Now, let's say here that we've got a focal length, it's got a shorter focal length, generally. Let's make this a little farther out there. And it generates a virtual image there. And so to find the magnification, you're comparing the angle made by the eyepiece, the tip of the virtual image, to the angle made out to the object from the same point, the ratio of the eyepiece angle to what it would be without anything using magnification. Now, what happens if we move the object to a distance of infinity, which is effectively the case in astronomy? We're dealing with things that are, in my case, billions, tens of billions of light years, well, not more than 13.7 billion light years away. Anyway, 10 billion light years away, effectively at infinity. As you move the object farther away, look what happens to the ray tracing here. The image, the real image made by that object, by the objective lens, moves closer and it gets smaller and it gets closer to the focal length of the objective. When that happens, then, okay. Let's take just the ray going from the tip of the object. Okay. You create then a real image, and it's going to move to the focal point of the objective lens. Now let's see, where's the focal point of the objective? There. But then what we're going to do is we want the virtual image to be infinitely far away as well, simply magnify it. So we're going to move the eyepiece in until its focus is in the same place as the objective's focus. So we get their focal points to match in the same spot. And when that happens, we get light rays that are coming out that are parallel to each other but at a very large angle. And they would converge at an infinitely far away, distant virtual image. So we compare this angle, theta of the eyepiece, to the angle made by the distant object, theta of the objective, there, and that ratio gives us the magnification again. In this case, in practice, that means that the angular magnification, which is the angle of the virtual image in the eyepiece to the angle of the objective, of the object at the objective lens, and that will also be equal to minus the ratio of the focal length of the objective to the eyepiece, which is a nice simple equation. And that's the end of this chapter. Like I said, I didn't want to go into great details on each of these applications because they're just applications. The rules are the same for every one.